Hi, I'm Larisa. I'm a first-year PhD student at the University of Edinburgh in computer science, and my project has to do with developing higher-level abstract frameworks for stencil applications like Room Acoustics Codes. The main motivation behind my project is that the HPC architectural landscape is getting quite complicated. If you want to run your code on new types of architecture like the Xeon Phi, FPGAs, writing portable code is quite difficult. You might have to maintain multiple code bases. Computational scientists shouldn't have to focus on optimizing code and retuning things for new architectures. So it'd be good to have kind of a method of writing portable code that maintains performance across different architectures. OpenCL exists as a portable solution, but the performance is not portable, and it's a very kind of low-level approach with lots of boilerplate code. So I'm looking into developing solutions that could possibly decouple parallel instructions from the algorithms themselves that could then kind of be more easily translatable across architectures. So in the first instance, I'm focusing strictly on room acoustics codes. So looking at how sound, looking at discretized rooms and how sound propagates through the room, kind of using 3D wave equation at points in the room. I've done kind of a low-level analysis of different implementations across different architectural platforms, looking at the performance, the portability, and programmability of these different versions. And I've also developed sort of an abstract version of the code I'm working with to kind of tune different parameters on different platforms to see kind of how well these optimizations can be transferred. This is a graph of sort of preliminary results that I have. So it's sort of split up into different architectures that I've looked at. So on the left, we got AMD GPUs, NVIDIA GPUs, CPU, Xeon Phi, and then looking at sort of 5 or 6 different versions of the same code using like OpenCL or CUDA or different libraries to kind of see how well the performance works. And so the main kind of takeaways for these this analysis is that the codes these room acoustic codes are memory bandwidth bound. The line kind of on the graph represents the stream benchmark, which is sort of like, you know, a good baseline of what you could be able to achieve. And as you can see, all of the codes are kind of quite far away from that. So there's a lot of room for improvement. I looked at some different data abstractions of the grids themselves, and on these, the performance for these across some of the different architectures is quite detrimental. And the optimizations that I looked at are not always straightforward to port. So I'm now kind of looking at more advanced room codes and comparing these to the simple ones, so adding things like viscosity in the room and boundary conditions and more complicated stencils. I'm experimenting a bit more with local memory on the GPUs to try and get some better bandwidth, as well as looking into some higher level frameworks that kind of currently exist but haven't really been tested on larger things, so kind of strictly on simple benchmarks. And then finally, I've been focusing on room acoustics for now, but in the future, hopefully I'm looking at other types of stencils and seeing how well these compare with room acoustics.